How quadcopters they work, how they fly. I'd like to talk a bit about my project, what I want to do, and then I want to talk a little bit about what other people have done, similar stuff. Then I'll talk about a little bit about how I did it, stuff like that. So a quadrotor has 4 propellers. I'd really like to have my pointer now, but don't. All right. So they work by, they have 4 propellers, and when the propellers in the back speed up, it tilts forward. And when the propellers in the front speed up, it tilts backwards. And the same for sideways. And when it's to rotate, the propellers in each corners rotate the same way around, and in the other corners they rotate the other way around. So by speeding up the propellers in 2 of the corners, it can rotate rotate one way around, and by speeding up the other propellers, it can rotate the other way around. And of course, it can lift and descend by speeding up all propellers at the same time or slowing down at the same time. Right? So what I want to do is I want to make a quadcopter that can that is capable of stabilizing itself without help from a human. Because normally you fly these like RC cars with a huge remote. But that's a little bit too unspecific to say I want to make something that's autonomous. So the goal here is that I want to make a drone that can autonomously fly through one of an opening of 45 centimeters in width, which may sound a bit specific. That's because it is. It's one of these RoboCop gates that I want to fly through. So what does this drone have to have on it to be able to do this? Well, first of all, it has to be small because these gates are quite small. So that's why I've taken this size. It's 30 centimeters across, and then I think it's 35 this dimension. It has to be self-contained. That's one of the rules for the RoboCop, that you cannot have a computer outside with all your processing power, and you can't have external cameras, and of course you can't have a guy remotely controlling it. So it has to carry all the stuff on it. And then to be sure that if something goes wrong, it doesn't fly out and kill people, I also have to have some sort of backup plan so I can take over control it manually, even though it's supposed to be autonomous. So there are some other people who have made similar stuff. There are some German guys at the Technical University of Munich. They made a system based on the Parrot AR drone. It uses the onboard camera and then an external computer for localizing using something called the PTAM algorithm. But yeah, it's not self-contained, and the drone is a little bit too large. It's about half a meter across, so it wouldn't fit through the gates. So I couldn't just copy their system, which would be a bit boring as well, I guess. Then there is this. It's not a complete system. It's something called the Pix Flow sensor. It's something that helps the quadcopter navigate, so it's sort of like a camera solution that you put beneath it. It works kind of like in the same way that an optical mouse works. So by detecting how the ground moves, it can detect how the drone moves. But then first of all, it wouldn't be that fun because it's already made, so I don't get to make all the things myself. And I've also heard that it doesn't work so well, but I don't know about that. And then there are some commercial systems. They are usually quite large and very expensive. This here on the right is from Zurich. They use external cameras. That's why it has those ping pong balls. So the external cameras can locate the ping pong balls and then tell the drone where it is in the room. The other one is, I think it's called the Pelican or something. It has a laser scanner as well, and I think it's about this size, so it's also way too big for this. So that's not really an option either. So what I have done is that I want to make some visual odometry, which is the navigation based on a camera, which I have here, and then on an IMU. An IMU stands for Inertial Measurement Unit. It's an accelerometer and a gyroscope in a package that allows you to determine how you're facing in space, what your attitude is. So with that and the camera, it should be possible to navigate, because that's roughly what we humans have. We have eyes, and then we have the IMU is kind of like your ear, the inner ear. So originally I was going to use something called the multi-state constraint Kalman filter for navigation. It's a long word, but it's basically just, it segments out features in the room, and then based on their position and their previous positions, it figures out how you moved. Yeah, and then I'm going to reuse an attitude controller that I made for a previous course. I'm going to show that a bit later. So what I have on my system is I've split the controller up in two parts. So I have an Odroid, which is it's just a small Linux computer. It's the same processor found in modern smartphones, but just without the screen and all the phone stuff. Just bare PCB with a processor on it. And to that I have a camera, which is the PlayStation 3 eye camera, because it's cheap and it's lightweight and it's I mean it's not super good, but it's okay. And then I have a Wi-Fi connection so that I can talk to it from my computer. I'd also like to be in future. I'd like to be able to stream back the video from the drone to my own computer. And then I also have on it. I have the flight controller, which is a real-time processor. It's a small ARM processor, and it handles stuff like motor commands. It handles sensor inputs from the IMU. I have a distance sensor as well, so I can figure out how far I am from ground. It samples that as well. And basically, it also has a radio, so if things go wrong, I can with remote control, I can shut off communication to the Linux computer, and I can steer it from the flight controller itself, just like you would with a regular quadcopter. So this multi-state filter, it works on a sliding window of images, which is that it saves the previous 5 or 10 images that it saw, and then it finds features in those images. And from those features and from where it thought it was at those points in time, it will try to estimate the 3D position of those features. But that doesn't work so well when you have a bad camera and you're shaking a bit and stuff like that, because then it's difficult to estimate the depth of the features. So what I did initially was that I was pointing the camera down, and then I said that all features had to be on the ground. So here we have, this is trying to explain how it works. So these boxes here are how the drone moves, and these boxes here are how the drone think it moves from previous estimates from the IMU and previous images. And so the camera here looks down on the ground and they see a feature here. But because they are moving, so they basically take and figure out what is the average of where I've seen this feature, which in this case is here. And so they take and compare where the feature was seen and where the feature is estimated to be in space. And as you can see here, the feature is closer to the center position. So this one would be told to move a bit backwards, and this one would move a bit forward. And because the way the filter works, it has some covariance between these states, so it would just move. Let this one be static, and then move these two a bit back. Does that make sense somehow? Okay. But it's a large algorithm. It runs very slowly, and because it runs so slowly, it doesn't really work very well. So I had to come up with something different that works a bit better on a small computer. So what I did is I just compare the previous image to the current image, and then my attitude and my altitude, I know those pretty good because I have direct measurements on those from the IMU and from the distance sensor. So from that, I take all the features that I've seen in those two images and I project them down on the ground. And then I figure out what is the closest geometric transformation between those two sets of points. And then I compare that transformation with how the drone moved. And that works. It's really simple. So here we just have, let's see, we have, this is how I move, this is how I think I move again. And just for a single feature is seen here. And then when this feature seen from one camera frame and the other camera frame is projected onto the ground, they end up here and here. And so it says that, okay, this feature should not move, but it did, so that means I have to move back my current state. And this can run at about 15 to 20 hertz on the small Linux computer that I have, which is enough to stabilize it. So far I've made mechanical construction of the drone. If anyone wants to see it, it's up here. You can come up and look later. And it's not put together at the moment because I had to redo some PCBs this morning. Actually, I'd like to have flown it now, but to show you. But yeah, I'm not going to put it together and fly with it without testing it before. So, and then I have the visual odometry working on this platform on the drone, and I have an altitude controller working on the flight controller. But what I still need is that I still need to be able to send data from the Linux computer back to the flight controller so that I can actually steer it from the navigation data. But hopefully I'll get that done today or tomorrow, or at least before Wednesday. And then I have to make a line follower, but that shouldn't be that difficult. I mean, I have a camera that's looking down onto the line, so I've done that before. Any questions? No? Okay. Oh yeah, I promised to show the altitude controller. There'll be a little bit of sound on my computer, but it's mostly just noise from the motors anyway. This was a 3 weeks course I did with the guy I'm also in Robocop with. And it's on a string because then we would be able to test it and have a power supply in it, and we could do stuff like that without it flying up in the ceiling. Yeah, that's basically it. All right. Thank you.